to describe here. So once you get the picture here, so you can see what I mean by now. When I said that I'm trying to describe the wave, which is in our case is just a pulse, maybe like this, okay? And what's happening is that this pulse again looks the same, except it's traveling in this case maybe to the right, something like this, okay? So it's moving to the right, this pulse of wave. That's what we are trying to describe mathematically. Okay, but remember that the whole thing moves, continuously, like in the simulation that we just saw earlier. Okay, so what's happening here? Well, let's say for each line here, the shape of the function is described by this mathematical object. So let me set up the axis here. And let me call the y-axis to be y, and then x-axis to be, let's say, x here. Okay, and one line here is described by a function f of x. Okay, so this is f of x. So let me label it by this yellow one here. So f of x describes the function which is in yellow. But as you wait for some time, this yellow thing, the whole thing gonna move to the right a little bit. So it becomes the green one here. Right? So except for the fact that it's not in the same position, the shape of the green one and the yellow one are the same. Right? And then later on, it's keep moving like this. Okay, so the shape is still the same, but it's moving to the right, like this. Okay, so how are we gonna describe this? Well, hopefully you remember from, I don't know, your previous class in any mathematics class. If you want to displace the graph, what do? You add or subtract your x variable by how much you want to displace. Right? For example, if I have the yellow one to be given by this function, right? The function for the green one here is f of x. Okay, and this is maybe something that you don't remember. Going to the right, you have to subtract something here. You have to subtract x0. Okay, and what is x0? Well, x0 is how much you move to the right. So if you mark the top of the wave, and the top of the wave move by x0 to the right, then the whole function is f of x minus 0. So how does it work? Well, for example, we can assume this is not going to be entirely accurate, but it's good enough. So let's assume that f of x is given by this particular function. So it's an exponential function. So e to the minus x squared. Okay, so that's for the yellow one. So let me mark with color here. The green one is f of x minus x0. So that means everywhere you have x, you have to replace by x minus x0. So that means if it's exponential, then it's going to be exponential of x minus x0 like this. And then square. So the shape of the function, how the function looks, is the same as before, except you replace everywhere with x minus x0. And just to remind everyone again, x0 here, this is the distance. that the wave has traveled, okay, so to the right. Actually, there's only one L maybe, I don't remember. Okay, so that's how much the wave is traveling to the right, x0 here. And for the blue one, it travels for another distance, let's say x1. So you know by now how the blue one gonna look like. So the blue one, or this is the green one. So the blue one is essentially just f of x, well, minus x1 and then minus x0 because it moved all together for the distance of x0 plus x1. Right, so the whole thing gonna move like this, and the function gonna look like this. Okay, so again, this thing here, the one you subtract, is the same thing as before, which is the distance that the wave has traveled. And if the wave is traveling to the left instead of to the right, right? So what you do is like you just flip the sign here. So instead of minus, you become plus, right? So that's probably the counterintuitive thing is that you go to the right, it feels like you increase x, right? So x just increase, but it's actually you have to subtract from x. So x minus something means it's going to the right. X plus something is going to the left. Right? So I'm gonna write it here. So f of x minus x, this is the whole thing, move to the right hand side. But if you have f of x plus x0, then the shape move to the left. Okay, so going to the right or going to the left is kind of just flipping the sign here. So we gonna talk exclusively about the wave going to the right, but you should remember that to flip the direction, you just you just change minus to plus here. Okay, hopefully so far so good, right? So this is true for any function that you have, right? If you have like a crazy looking wave, maybe something like this, and somehow you can describe it by some function, and the whole thing moves to the right, then again it's the same thing. You just replace x by x minus the distance that you have moved, right? But the distance that this wave travel depends on how long you wait, right? So if you wait long enough, then the distance is going to be really, really large, right? So what I should write down here is x0, which is the distance that the wave has moved, in this case to the right. Okay, so x0 actually depends on time. And I can write it in this way, v times t. And v is what we call the wave velocity or the wave speed. Doesn't really matter whether you call it wave velocity or wave speed, especially for one-dimensional wave, which is wave going in one direction, left, right. Okay, so I'm gonna use the two kind of interchangeably sometimes, but just remember that it's the same thing. It's just telling you how fast the wave is moving. Okay, so the wave velocity is given, and time here is the regular time, is how long you wait. Right. So if you wait long enough, then the whole wave gonna move to the right by a lot. If you don't wait long enough, then it's not gonna move that much, right? So that means if you want to describe the wave at any time, okay, at any time, you have to replace x to be x minus x0, right? But x0 depends on time. So I should write something like this, x minus vt. And this whole thing is the argument of the function, right? So if we use the same functional form as before, which is the, minus x squared, e to the minus x squared. So that means if we were to describe this wave at any time, then f of x minus vt gonna look like e to the minus x minus vt, the whole thing square. And this is nothing new because you just replacing x0 by vt. That's it. Right. So the fact is that x0 is not constant because the wave moves all the time. Right. So x0 also depends on the time. And again, if you want the wave to move to the left instead of to the right, then you flip the sign here. So that's going to be f x plus vt, right? So that's going to be wave going to the left instead of going to the right. So everywhere that you have x minus vt, then you write x plus vt instead. Okay. So everywhere that you have that sign, then you just flip the sign here. And this is true, again, for every function that you can have, right? Again, because if you want to shift the function left or right, what you do is you just replace x by x minus x0 or x plus x0. And in this case, x0 is vt. So in terms of wave in general, any function that can be written as a function of x plus minus vt. Okay, so I'm trying to be general here, so it will include both signs. So any function that can be written as x plus minus vt, function of x plus minus vt, is a wave. If you can't, then it's not a wave, right? So this is purely from the mathematical kind of language, and we're gonna restate this again in a maybe more mathematical way, but this is essentially what we mean by the whole discussion here, is that if you have any function which can be written in this form, then it's a wave, because it means that the shape of the function stay the same, but the function just shift to the right or shift to the left. Okay, and that's exactly what we call wave. Okay, so as an example, the one we had earlier, y equal to, well, just to be clear, y of x minus vt equal to e to the minus x minus vt. This is a wave because it can be written in terms of x minus vt, right? So I'm gonna write this in a little bit more general way. So you can see that this function y here depends on two free variables, which is kind of the first time that we see this in our physics class, right? So usually you have like position depending on time, so x as a function of t, or you can have the energy depending on the location, like the potential energy, so EP depending on the height h, right? But this is kind of the first time that you have a function y that depends on two free variables, x and t. So sometimes instead of writing this, we're gonna write y as a function of x and t like this, okay, to indicate that there are two free variables, x and t, that you need to worry about. Just knowing x alone is not enough, and knowing t alone is also not enough. You have to know both of them to be able to fully describe the wave. Okay, so if y of x and t can be written in terms of y of x plus minus vt, then yes, this is a wave. If not, then it's not a wave. For example, if you just say y equal to sine of x alone, this is not a wave, because where's time? Time is not appearing in in the function. So this is not a wave. Okay. Or you can say y equal to sine of, for example, omega t, which is what? The motion of the simple harmonic oscillator that we talked about in the last lecture. It should be very related to wave, but somehow it's not a wave because there's no x. So this is also not a wave, right? It's oscillating in a simple harmonic way, but it's not a wave because wave also have to include, propagation of the oscillation, something like that. And that's, believe it or not, it's captured in this mathematical form here. Okay, but if you have something that can be written in terms of x plus minus vt, for example, x minus vt, the whole thing square, this is wave because you can have x minus vt altogether like this. Right. So sometimes it can be a little bit hard to spot. For example, I can have x square plus vt square. Is this a wave? It's actually not. Even though both x and t appears in the equation, but you cannot write it in terms of, x minus vt to the power of 2 or something like that, right? So if you cannot group x minus vt all together and somehow not have any x and t left in the function, then that's not a wave, right? So it's actually a very strict class of function that we can call it as wave. Okay, so in general, anything that behave or can be written like this is a wave, right? So that is infinite possibility that you can write down. So of course we're not gonna study every possible functional form of wave because that's gonna be, nonsense, right? Because like how can we have enough time to do everything? So we're gonna pick the easiest form of wave to study. And just like for oscillation, the easiest we can study is the sine motion, so sinusoidal motion. So that's the simple harmonic motion. For wave, we're gonna study what we call sinusoidal wave. So sinusoidal wave is actually just mean wave which is described by sine function. Okay, so sinusoidal is kind of like the adjective of function sine, but it also can be cosine, right? Just like what you asked last time, like why do I have to use cosine? Is sine okay? They are equally, they're equivalent to each other. Okay, so how do we describe sinusoidal wave? Well, we need to again set up some coordinate here. So gonna do it like this. And well, actually, I want to do it later because I want to copy something. So I'm gonna draw a sine wave to the best of my ability. Something like this. So I'm using the grid as my guideline, which is gonna be important later. Okay, something like this. And what I want to do, I want to copy this to be used later. So I put it there first, and then I gotta put the coordinate here, because if I put the coordinate later, then I have to copy the whole thing. I don't really want that. Okay, so ignore this for now because I'm gonna use that later. So what are we seeing here? Let's imagine that we have a piece of string and you are sending in wave all the time. So the wave looks like sine wave, right? So what we are plotting here in the horizontal direction, that's what we call x. And what is x? X is the location on the string. So where it is on the string that you're trying to describe, that's what we call x. Okay, so x has the unit of length, so in meters or millimeters, something like that, right? So it's the position on the string. All right. What about y? Y describe how far away each section of the string displaced from the center line, right? The center line is this line here. The center line is the line, the horizontal line, where the string would have been if there's no wave traveling in the string. Okay, so it's kind of like an equilibrium position for the mass and spring system that we talked about last time, right? So if it's not oscillating, that's where the particle gonna be. So y measure what we call the displacement, okay, of the string. The displacement of the string. For example, if you pick one particular point of the string here, the displacement is the distance, what, not the distance, the displacement from the center line. So it's going to be that displacement. If you pick this one, the displacement is a little bit smaller, okay? And if you pick this particular point here, that just happened to have zero displacement, okay? But as the time goes on, the wave gonna move, so the section of the string that used to have zero displacement will no longer have zero displacement. So it's gonna move up and down. Okay. All right. So if this is wave, it's not gonna look like this for all the time, right? So I can say that let's assume that we are taking a picture, right? You take your digital camera and you snapshot the wave on the string every second. So let's say this is when you take the first picture, and let's call this t equal to 0, right? So that's where you start your timer. And then after 1 second pass, you take another picture and then you put it here, right? So let's assume that after 1 second, the wave move to the right a little bit. So it used to be here. So after 1 second, it's gonna move a little bit to the right like this. Okay, so you see what I'm getting at. So if you wait long enough, it's just gonna keep on going like that. Okay, so after 1 second, let's say the wave is here. Another second pass, then it's gonna be here. Another second pass is gonna be here, right? So I'm just putting this in a sequence, and I'm very careful in, putting it at the right spot here. And I actually need 5 pictures, which I have already. Okay, so this is t equal to, I actually can remove this. So this is t equal to 1, t equal to 2, t equal to 3, and then t equal to 4. Okay, so the time here are kind of arbitrary. So it doesn't have like 1, 2, 3, 4. It can be, like 0.1, 0.2, 0.3, or any number. It's just important that I'm putting like equal time interval for each picture here. All right, and the wave is not just this particular section, right? Because I have to kind of fill in the blank so that the wave kind of is not cut or anything. So something like this. Okay, so that's the wave at different time. So what are we trying to do here? Okay, so let's first pick the same x. Okay, pick the same x means we're gonna pick x here maybe. So let's pick this particular spot here. Picking the same x means I don't care if the wave is moving to the right. I just want to follow the same x. So here it's gonna be here, 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 and then here. Right. So this is what I mean by the same x, which is this green points here. So you can imagine if you just follow this particular green spot, which is on the same point on the string, right? What's happening here is that the green dot here will just oscillate down, right? So it starts here, now it becomes at the center, now it's down here, now it's back to the center, and then it's back up here, right? So it's oscillating up and down. And from t equal to 0 to t equal to 4, this particular point here has complete exactly one cycle of oscillation, which is the up-down oscillation. And that's true for any other spot. You can pick here, here, you can pick this spot, right? So that's going to be the same for every spot that you pick. Okay, so we can say that from here, t equal to 0 to the last one, this particular oscillator, the green dot here, completes one period of oscillation. Okay, so the green dot here, so the green dot completes one oscillation from t equal to 0 to t equal to 4, right, in this particular case here. And how long does it take to complete one oscillation? Well, last time we have a special term for that, right? That's what we call a period. Okay, so to complete one oscillation, the time taken is exactly one period, or 1t. So we are looking at each dot on this string as a simple harmonic oscillator. So when it completes one oscillation, the time it takes is one period, 1t. Okay, so that's fine. Let's just put it here and then let's switch our view a little bit. Now I'm gonna follow not one particular dot on the string, but I'm gonna follow one particular dot on the wave itself. So what do I mean by that? So let's pick the same dot here at the starting point. Now I'm gonna put it in red. But now I'm gonna follow the peak of the function all along the wave at different time. So I care about this dot here, and here, and here, and here, right? So the dot now move along with the wave like this. And what you can see is that after you have reached the bottom picture, the red dot moved by how much? Well, it moved by this much. Because now the red dot is aligned with this line here. Okay? So that's the distance that the red dot has moved. In wave, the distance from peak to another peak in wave is what we call the wavelength. So lambda is called the wavelength, which is the distance to the same spot on the wave. Well, I should say the shortest distance to the same spot, because you can also go here, which is looking the same also, but that's not the shortest. The shortest is here, lambda here. Okay, this is called lambda, which is the wavelength. So you can see that in terms of the distance traveled by this red dot, after time, well, starting from t equal to 0, and then finish at time equal to 4, the red dot here moved by 1 lambda. Okay, so now instead of looking at the green dot, which is the cycle of oscillation, we're going to look at the red dot. So I'm going to write red dot here. So red dot travels by lambda, or maybe I should say by a distance of lambda, okay, from t equal to 0 to t equal to 4. So remember that the red dot and the green dot movement, they happen at the same time. It's just we choose to look at two different things which is happening at the same time, right? So if you look at the red dot moves to the right by 1 wavelength from t equal to 0 to t equal to 4. But for the green dot is not moving, because the green dot is just following the same location on the string. The green dot is just oscillating up and down. Right? So the green dot complete one cycle of oscillation from t equal to 0 to t equal to 4. So in other words, the green dot gives you the information of time, how long it takes. The red dot gives you the information of distance, how much the wave has traveled. So combining these two, I can write the wave velocity or wave speed. So the wave speed, v, is just distance divided by time. Okay, the usual definition of velocity, distance divided by time. And again, distance is lambda, because that's how much you travel. And how long does it take is 1 period. So we have this very important relation between wave velocity or wave speed and wavelength of the wave and the period of the wave. And sometimes most of the time actually, we're going to use, instead of period, we use the frequency of the wave. Okay, so frequency is just 1 over the period. So that's why most of the time, some of you might have seen this already. You're going to see this formula here, v equal to f lambda. And then it's a little bit kind of hard to understand, like, why do you have like frequency appearing here, right? So it's not as clear as writing it this way, because you see right away that velocity is just distance divided by time. But we're just rewriting the time, which is 1 period, to be the frequency. So v equal to f lambda here, right? So this is kind of like a very kind of detailed, maybe sometimes overly detailed, but I hope it gives you a nice picture of like how this formula is derived, right? So it's very important. I would say it's really worth remembering, because most of the time you gotta get asked like, what is the velocity of the wave if you know the wave frequency and the wavelength, or you're given the wavelength, you're given the velocity, then you're asked to find the frequency, right? So this one is the one that you need to use, and I use the sinusoidal wave to derive this, and it looks like it might apply only to the wave on the string, but it's actually true for any kind of wave that we're gonna study, right? So sound wave, light wave, electromagnetic wave, all obeys this formula here. So V equal to F times lambda. That's very, very important here. Okay, so I think it might be a good time to take a break, and we're gonna come back and talk a little bit more about the mathematics of wave. Okay, so let's take a 10-minute break here.